Good day. This is a short lecture on test-driven development as part of software engineering in practice. My name is Rob Sabre. So I've been involved in software engineering for quite a number of years, having written my first code in the early 1970s and completed my first commercial software release basically in 1982. I started doing commercial software development actually in 1979. So this is been a long time I've been at it. I've worked in a lot of different practices. And one of the practices in software engineering that is sort of close to my heart is the notion of testing as part of software development. And test-driven development came up as a programming approach, which I first heard of in the 1980s and 1990s. It was a practice where programmers were encouraged to create their unit tests for the code they were going to write before they wrote the code, and then wrote the code to pass the unit tests. So the idea would be to create the unit test, to run the unit test, it would fail, then you write the code to pass the unit test, then it passed, then you move on to the next unit test. And eventually, after you've exhausted all the unit tests you selected, you could say that you're finished implementing whatever you set up to implement. It's sort of a programming approach where you divide your programming activity into small chunks of functionality or capability or algorithms that can be tested with very specific unit tests. And you do this incrementally, and eventually you have a system that does the job. It's a programming approach. So test-driven development is not a testing approach. And it's not a new approach, but in the last 5 years, its practice has taken off quite a bit. In the early days of test-driven development, I would suggest, as I said, in the late 1980s, early 1990s, there was a lot of people advocating the idea, the concept, the approach. And if you went to a development or a testing conference, you might see people wearing T-shirts with a picture of a horse pushing a cart. And in the picture would be text that says, test first, code later, instead of code first, test later. So test first, code later. Only write code to get tests passing. This test-driven approach. It's unfortunate that in the early days of test-driven development, even though there were great documented approaches to doing it, and Kent Beck started to champion it and even wrote books on extreme programming, all of this predating the Agile Manifesto. We're talking about the mid to late 1990s, all this wonderful reference material on test-driven development coming out. However, the practice was awkward and tricky to say the least. And the project teams that I was working with, and I was a software engineering director and manager during those period of time, so I had lots of programmers working for me, and many of them wanted to do test-driven development, but we ended up spending tons of our energy building hooks, building frameworks, building tools to facilitate test-driven development. Test-driven development wasn't naturally done with the integrated development environments which we had at our disposal. They were things that we always had to sort of instrument ourselves. Now, if a programmer is a toolsmith and the team has people who are tool makers, then that might be a natural approach. But actually, it was distracting in many of the projects that I worked on in the early days because the programmers really wanted to get down to solving the problem at hand rather than figuring out how to make a test harness work. And these test harnesses were very important because you had to be able to repeat the tests over and over again while the application was being developed. And the application being developed was like a moving target for the tests. So you spend tons and tons of time in those early days maintaining your tests, maintaining the tools you were building, and it was distracting for the programmers. And so it wasn't really everybody who bought into that approach. However, in the mid 2000s, we see the advent of dramatic improvements in tools for software engineering and software engineering development environments. And with these more modern tools, we see really seamless integration of test-driven approaches. So now, today, almost every modern IDE on almost every imaginable platform, including mainframe platforms, Linux-based platforms, Unix systems, Windows systems, Mac systems, all sorts of proprietary systems. We see built into them integrated development environments that support automating unit tests as part of the programming process and facilitates, to a large extent, test-driven development. So the programmer can get on with the job of solving the problem. Test-driven development becomes an approach to programming, and the developer does not have to spend all of their time figuring out how to sort of hook the unit test into the code and integrate it and repeat it over and over again. So today, tool support for test-driven development is very good, and today the practice is growing. In fact, there's even some academic organizations which use test-driven development as an approach to teaching programming languages. Most notably, in North Carolina, there's a university which teaches Java programming with test-driven development. And if that's how you learn Java programming, then pretty much the only way you know how to do Java programming is through TDD. So you're building your unit tests, your JUnit test, then your code, then your next unit test and your code, then your next unit test and your code. And at the end of the coding, you've actually got a lot of unit tests written, which can be used for structural regression testing down the stream. So it's pretty handy to do that. Kent Beck is a champion of test-driven development. He wrote the book called Test-Driven Development. He champions extreme programming. He wrote the book called Extreme Programming. And on his website, extremeprogramming.org, which is like a community website for extreme programmers, you'll see a nice description of TDD. And I'd like to quote this because I think it really captures the essence of test-driven development, and maybe even some of the risks with test-driven development. So this is quoting the text from Kent Beck. There's a rhythm to developing software unit tests first. You create one test to define some small aspect of the problem at hand. Then you create the simplest code, the absolute simplest code that will make this test pass and no more. Then you make a second test. Now you add to the code you just created to make this new test pass, but no more. Not until you have a third test. And you continue until there is nothing left to test. So you don't write any code unless you have a failing unit test. And you know you're finished when you have nothing left to test. The problem, of course, is that testing of software is indeed an intractable problem. And for even the simplest piece of code that you're trying to write, there's an infinite number of possible tests at your disposal. The work for Edgar Dijkstra did, the famous mathematician in the 1960s and 70s, demonstrates very clearly that software testing can show the presence of bugs, but software testing cannot show the absence of bugs. There is no way to demonstrate by software testing that a piece of software is bug-free. So the statement, you continue until there is nothing left to test, is quite open-ended. And this is a subjective thing because you can keep going forever and forever and forever. There are an infinite number of conditions and environments and factors that can go. So what I would urge people to do is, if they're practicing test-driven development, is before you start the programming, to sort of figure out what is the scope and make a reasonable list of what your unit tests would be or should be to be good enough to get the job done. And good enough could be quite robust. I'm not suggesting good enough means flaky, but this is something that we've got to do deliberately before we start doing test-driven development. It's not arbitrary because every single programmer in the team might have a different subjective assessment as to what is enough unit testing. So I think it's important for people to do this as a team beforehand, before you start programming, to get a good sense of what is a reasonable set of unit tests for a piece of code being developed. That said, every organization does things differently. One of the world champions for test-driven development is Elizabeth Hendrickson. She ran a consultancy on software quality assurance and testing for many, many years, and now she's an executive officer at the company called Pivotal in Silicon Valley, where they practice test-driven development rigorously, and they also, I believe this is complete, all of their projects use test-driven development all the time. So it's all test-driven development all the time. If you want to become a programmer at Pivotal, you have to demonstrate that you're able to do test-driven approaches. It's quite interesting to see that even people who are not programmers need to understand test-driven development. And Elizabeth Hendrickson has a fascinating way to describe test-driven development so that non-programmers can really grasp it. And she basically uses a simile comparing it to writing articles. So here's her sort of perspective on it. There's a quote from Elizabeth Hendrickson. When practicing TDD, I use each test as a way to express an expectation about the code that just isn't true yet. Then I make the expectation true. I refactor the code. Every time I've got a new passing test, I refactor the code, clean it up, and I move on to the next expectation. It's a little bit like writing an article by deciding what question to answer next in the prose. And I run into, of course, many undergraduate students in my classes that have an awkward time of writing essays and articles. And I say, well, think about test-driven approaches. Before you start writing your article, brainstorm. Brainstorm with your peers, brainstorm with other people in your team, brainstorm with your classmates. Come up with a nice list of questions that you want the article to answer. And then treat it like test-driven development. Choose a question. Choose your first question. Choose your favorite first question, whatever you like. Pick one. Answer it. Write 1 or 2 sentences to answer the first question. Then get a second question. Write 1 or 2 sentences to answer the second question. Then refactor. Take the text you wrote for the second question and the first question. Make them consistent. Make sure that they have common, for example, term usage, common grammar. It's in the same tense. It's in the same literary style. You define terms before you use them. You express things in the correct order. And so you clean it up a bit. So you add a little more. The next question, answer, refactor. Next question, answer, refactor. Before you know it, you've answered all the questions and you've actually written a beautiful article. And so this is basically, it's a simile. Test-driven development is like writing an article with the questions first. I have actually tried this. I've done this twice so far in articles that have been published, and it's an awesome way to express things. It's an awesome way to solve complex problems. You avoid writer's block. You get things done. And you can also look and say, well, okay, so far, if you say, what's your % done on writing an article? Do you want to say, well, it's a 3,000 word article, I've written 1,500 words? Or would it be more interesting to say, well, there's 40 questions we wanted to answer, and right now I've answered 20 of them, so there's 20 more to go. I think the number of questions answered versus to go is a much better feeling for your progress than the counting of the words in the end. Or maybe it's just me. I don't want to be too cynical about metrics. But I do think that Elizabeth is a beautiful way to express what is test-driven development. So in test-driven development, we like to say, begin with the end in mind. By the way, that's also quoting a guy called Steve Covey, who wrote The 7 Habits of Highly Effective People. And the first habit that he tries to express and teach people is begin with the end in mind. Know what it means to finish before you start. If you read Alice in Wonderland by Lewis Carroll, he talks about the Cheshire Cat and Alice is trying to seek directions from the Cheshire Cat. And the cat asks, well, where are you going? And Alice says, I don't know. So then it doesn't matter which way you go. If you don't know where you're going, it doesn't matter which way you go. In test-driven development, we need to know what it means to finish before we start. We need to know what the tests are before we start writing the code. So the code is finished when we pass the tests. That's the sort of idea here. It's a pattern. You define a test, implement it, and when we say define it, it's basically saying, what do we want to learn about? Implement it, write some code using tool like, for example, JUnit. In Java, you'd write a little bit of code, and you would also put in that code an assert of what it means to pass or fail, or one or more asserts as to what it means to pass or fail that test. And then you create the absolutely simplest code to pass that test and no more. So we're talking about the simplest code and no more. No gold plating, just enough code to pass the tests and no more. Now, a lot of programmers are very good at software design. Software design is a hard thing to do, and people who take university degrees in software engineering do learn some software design approaches, mostly object-oriented software design approaches, where you take a big problem and you break it into smaller problems, and then take the smaller problems and break them into smaller problems till you get the problem to the size of something that can be created as an object, method, class, stored procedure, chunk of code, script, function, process, some element of a software engineering project, and then you recompose. So you decompose, recompose. Imagine the Russian dolls, right? Break it apart, put it together, break it apart, put it together. And once you've done this, you create a beautiful hierarchical decomposition of your problem, and you have a beautiful, graceful, symmetric object model that can be put together, and you can solve all sorts of wonderful problems that way. And a lot of programmers are tuned to designing using these methods, and it's glorious. It's very beautiful to see well-designed software, and I get to look at it every time. Every year when people do projects in my undergraduate courses, I take a chance to look through some of the code, and I almost always see graceful object-oriented design. It's really something that we see skills among professional developers that are great in that. However, when you're asked to design a testing problem, you're not asked to decompose the testing problem into sort of sub-problems and come down to some point where you have a parallel in testing to objects, methods, classes, and procedures and stuff like that. In software testing, what we do when we design tests is we figure out ways to identify a small subset of the really infinite set of possible things we could test. So we try to identify a small subset of what can be tested, that if we tested that subset, we'd learn something that would apply to the whole. And software test design is tricky at best. There's a lot of beautiful software test design approaches, and people study and learn them and master them, but they're not the same design approaches that programmers use. So I think, and in my experience, I think it's an excellent idea that before, for example, for a story in an agile team, before the story starts being programmed, it's probably a good idea for someone with testing or test design skills to brainstorm with the programmer about the potential unit testing ideas and what's the scope of unit testing, what are interesting risks to explore, and all those type of things. And that brainstorming activity usually ends up with a list or with a map, a visualization of some sort of the unit tests that a developer would then choose from. And I ultimately, I think it is up to the programmer to choose what unit tests and in what order they want to run them. But I think it's an excellent idea to pair with someone with test design skills before you start implementing a story with TDD. So before you start using test-driven development, take a look, make a good list of unit test ideas, and collaborate with people with test design skills so that you can be sure that you've got a reasonable set of tests and you're exploring and covering risks that really matter and are relevant to the business, technical, organizational, and cultural factors around the stories that you're implemented. So this would be considering that developers have great software program design expertise, but very often are missing test design expertise. Now, there are, of course, some developers who are masters of both, that are masters of test design and masters of program design, but not everyone. And it's very hard because it's a different thing. It's a context shift. Decomposition methods are different from focusing methods. Testing uses focusing methods for design. Programmers use decomposition methods for design. They aren't the same, not the same, certainly not the same mindset for the two approaches. Bob Martin, the pioneer of many wonderful aspects of software engineering. Many people see Bob Martin at Agile conferences. He's written many books on testing and on programming and test-driven development. And Bob Martin came up with the 3 laws of test-driven development. This is loosely modeled after Isaac Asimov, the science fiction writer's 3 laws robotics from the famous book or movie, if you've seen it, I, Robot. In either case, the three laws of TDD are really, really rules for developing code with test-driven development. And many programmers who practice TDD follow this quite rigorously. And when I do TDD as an undergraduate assignment or exercise, I use these as a basic for my grading rubric. So this is very important for people who are going to be practicing test-driven approaches when writing code. So the first rule, according to Bob Martin, the first rule is you may not write production code until you have written a failing unit test. So if you don't have a failing unit test, you can't write any production code. So that's the first law. No code until you have a failing test. And this is not just having a test, but having a failing test. It has to fail. Now, Bob says you may not write more of a unit test than is sufficient to fail. And he says also, like, not compiling is failing. So you may not write more of a unit test than is sufficient to fail. The suggestion here now is that the test should be incremental. So you're going to basically write just enough test to fail. So no code unless you have a failing test. When you make your next test, make it just enough test to fail. And then you may not write more code than is sufficient to pass the currently failing test. So just enough code to pass, just enough test to fail, just enough code to pass, just enough test to fail, just enough code to pass. And if you follow these three rules, you're going to now use incremental approaches, a little test, a little code, a little test, a little code. And at the end of a session of development, you will have really thoroughly structurally tested code. Many, many, many unit tests for the code, and you're pretty much guaranteed that the test has 100% code coverage. So this is basically every line of code that you've written has at least one associated unit test if you follow the rule of just enough code to pass the currently failing test. And of course, after each session, there's the refactor. So when you get a test passing, there's this notion that you should clean it up, and therefore you should be able to repeat your previous unit tests over and over again. So we don't just write the test and run it once. We write the test and we run it every single time we basically compile the code. We run those tests over and over again. Kent Beck teaches the mantra of test-driven development. Red, green, refactor. Sorry about the colors on this monitor are off. So red, green, refactor. It's interesting because the red one is coming up as blue, the green one is white, and refactor is green. So what we have is red means stop, right? So you start with a failing unit test. Green means go, so once the test passes, you continue. And refactor means after you've got a passing test, try to generalize the code. Try to clean up the code. So that's the mantra. Of course, the monitor color scheme is wrong, but the mantra is always true. Red, green, refactor. Red, wait for a failing test. Green, write just enough code to pass the test. And then when you get a new passing test, refactor. And when you change the code, run the old unit tests over again to make sure you didn't accidentally break something. There's a lot of tools and mechanisms to facilitate the unit testing being done at the time while we're doing TDD. Many frameworks will support the automatic execution of unit tests, JUnit, NUnit, every imaginable unit testing framework. There's tons of them available. They couple with your development environment. They integrate transparently, usually with the IDE and the source control system and the build environment. Ideally, every time the software is built, you want to repeat your unit tests over and over again. And this, of course, means that you should structure them so that there's like limited dependencies on data and things like that. So you want to basically structure them so repeatable. And then people have different types of dashboards. In fact, there's a wonderful instrumented dashboards available on the market today. I would say, I used to say there were dozens, but there's probably hundreds of them right now. And they're just fantastic. They show you information about what tests have passed, what tests have failed, and for the tests that have failed, what code has changed that's related to, and what check-in of code was that change related to, and what story being developed was that change related to. And you get the whole chain of dependencies there. So when you have a failed unit test, it becomes fairly straightforward to troubleshoot which check-in led to that that failure and gives you a good starting point for correcting it and reworking the problem. So this is a really awesome thing. These dashboards are getting better and better every day, and they really show you, very quickly how to identify the cause of a failed unit test or what's happened before a failed unit test. They don't really tell you how to rewrite the code, but certainly if you undo the changes, it'll go back to the initial state, the previous state. So that gives you sort of sense that something happened from the previous state to the current state. I somehow introduced the failure. And it might be a unit test you didn't expect to fail. A lot of times when I get this, I get a unit test failing that I thought had nothing to do with the code change I was doing. But in fact, there was some relationship. I just didn't realize it at the time I modified the code. There's some terminology that sort of funky that's been used in software engineering, I guess, since the dawn of time. I just remember learning these words when I learned how to program. So people would say, well, if a unit test fails during your test automation of the unit test, they would say the build is broken. So did you break the build? Getting a failing unit test is breaking a build. And the idea, of course, used to be that if systems would have builds, at least one big build every night, but you couldn't leave the building if your test failed. You had to fix it before you left, right? You can't leave it before, if the build is broken. You have to fix it before. Fix the build before moving on to the next development activity. If you stop the build, you're stopping progress, right? So fix the build. We call this build breaking great ways to detect problems introduced by change, i.e., the automated unit test is an unexpected change detector. Now, was that change good or bad? It depends. Sometimes when you have a failed unit test, it's because the behavior of the system is correct and the test of the system is incorrect. So to fix that, you have to change the unit test. Sometimes it's the opposite. Sometimes the test would be correct and the system would be wrong. And that would give you basically a need to change the software, especially legacy code. If you accidentally modify it, you get all sorts of ripple effects and see failing unit tests all over the place. What you've got to be very careful of is if you've got a failed unit test and then you modify the test so that it passes, even though the code is actually failing. And this is, of course, a nasty side effect. We call it a false positive. So when someone says, oh, the unit test was broken, let's fix the unit test, but they should have fixed the code, you get then a false positive. You get passing tests that are indicating the system is passing when it isn't really passing. So something we have to be very careful about. So when we change unit tests, it's a good idea to consider using peer reviews and other static techniques to help you to double check with other human beings to say, did you accidentally sort of create the situation where two negatives make a positive? So you want to make sure that the code is doing what it's supposed to do, that the unit test is checking for the conditions and asserting on the conditions that matter, and both of them are harmonious. Both are harmonious. I have a couple of related cautionary tales about people practicing different forms of test-driven development with unit testing. And the first one is the internship. So this is a story that took place a few years back at Google in Mountain View, California. And at the time, I was working with a person at Google called Goranka Jadova. And Goranka is a colleague of mine, a peer, professional friend. She was at the time responsible for performance testing at Google. She's since then she moved to Facebook. She seems to follow the world's biggest performance testing problems around. But while Goranka was at Google doing this performance testing in Mountain View, California, I was working collaboratively with some people at Google on designing methods of doing test design for Gmail. So I'm with my undergrads at McGill doing Gmail test design, and I went down to Mountain View to Google to meet with Goranka, discuss some of my test design stuff, share it with her, validate the approach, and take a look at some of their performance testing activities. I was very big on performance testing at the time. So while I'm there, I'm in Google, I'm meeting with Goranka. Suddenly, we find out that there's a group of interns, student interns, that are assigned to Goranka's group. Now, if you're familiar with Hollywood production movies, there's a movie called The Internship, which represents a summer internship program at Google. And it shows it as a competitive internship. In fact, the internship I witnessed was not a competitive internship. However, it was similar to the movie in some ways, in that there was a cluster of interns that worked together. So they were always together, this group of people, like 5 or 10 people, always together. And they stayed in one group for a few weeks, then they moved to another group. And so I was there by coincidence at the exact time when this group of interns was assigned to Garanka's team. And Garanka wasn't too fond of this obligation, although at the time that's what she was being paid to do as part of her job. So she, to keep the interns busy, basically gave them some work on some of the tools environments they were using. Google had at their time make their own tools for a lot of performance testing. In fact, Google is famous today for making software engineering tools to support their development effort. Many of them are put in the open source. At the time, Garanka's performance testing tools were internal to Google, and they were basically used to simulate load and study performance patterns of Google software running around the world. So the interns were asked to inventory the build servers and the build environment for these tools. Garanka wasn't the top of her priorities at the time, so she thought the interns would learn a lot from that and keep out of her hair on a day-by-day basis. Okay, so I'm continuing my work with Garanka. The interns go about their business, and about a day later, the cluster of interns come to Garanka and say, Garanka, we found a problem. And they explained to Garanka that on one of the servers, they had found the log of test results, unit test results at build time, and there were several hundreds of tests in this list. And there was one somewhere in the middle of the list, there was one failing unit test. And so they point this out to Garanka. So Garanka said, okay, well, what I'd like you to do is investigate this. Garanka asked the students not to fix the problem, but to try to figure out how to fix the problem, probably learning literally who at Google would be responsible for it, how the thing worked, reverse engineer software engineering at Google. So that was their assignment. So Garanka sort of gave the interns more work to do to help figure out what was wrong with this failed unit test and what they should do to fix it. But she didn't ask them to fix it. She asked them to come and tell her how, and then she would decide what to do. I continued my work with Garanka. We're looking at our test cases and the Gmail stuff and having a good time. And about a day later, this cluster of interns comes back again, and they're all proud. They're jumping up and down proud, and they were saying, Garanka, we found the solution to the problem, and we fixed it. Of course, Garanka had told them explicitly not to fix the problem, but they said they fixed it. They claimed they had fixed it. Okay, so let's take a look. So Garanka went there, she dragged me along, and the students basically showed Garanka a power plug on the wall. And he said, see this server, see this power plug? Well, this is the server that was running the software under test. So the software under test ran on a certain server. The server, they said, was not plugged in. They noticed this, so they plugged in the server, and then after the server booted up, the next time the unit tests ran, they all passed, such that they showed Garanka the log of tests all passing. Said, everything's okay now. We fixed the problem. Of course, Garanka, in her wisdom, asked them if they were sure that they solved the right problem. And she pointed out to them that previously they had hundreds of passing unit tests and only one failing unit tests, testing software on a server that was powered down. Now, how could you have hundreds of passing tests for software that was powered down? So Garanka went with them and started looking at the source code of the unit tests. And they found in that source code of the unit test, test after test after test, where the code in the test was actually commented out. In fact, it's pretty much every single test with one exclusion was commented out. Now, this activity led to the ironic situation that you had hundreds of failed unit tests and hundreds of passing unit tests which were doing nothing, and one failed unit test which was one that was trying to do something. Now, this activity actually has a name, and some companies call it deprecating. And deprecating a unit test takes place when you have an old unit test and it fails and the test is no longer relevant. And so what some teams do is they'll say, okay, this old test is no longer relevant. Rather than fixing the test, we'll comment it out. Now, this is a sloppy software engineering practice. You should, and this is what I recommend, you should fix the test or fix the code. And if truly you feel that this code is no longer needed and this test is no longer needed, then you should remove the test and remove the code that it's testing. And don't just leave it as a dangling thing there. If there's code that doesn't belong, get rid of it. If there's a test that doesn't belong, get rid of it. But commenting it out so that it looks like it's passing when it's actually doing nothing is giving people a false impression. Now, I don't want to put down or diss the practices of any one organization. This story was about internal servers of software that was used on internal tools that was not production software at Google, and it was not being developed at the time to the standards that production code was being developed to. It was sort of like disposable code for internal tools. That practice, I'm sure, is not taking place frequently at Google, but it's a cautionary tale. So when you have a failed unit test, fix the test or fix the code or both, but don't just comment out the test so that it looks like it's passing. And if you're removing the test, remove the code that it's testing at the same time. If we need the code, we need the test. If we don't need the test, then we don't need the code. Commenting out the test and leaving the code there puts you in a precarious situation. And you lose the regression confidence from the whole suite. So the whole suite becomes meaningless if you start deprecating unit tests. So that's one cautionary tale. I have one more cautionary tale about unit testing, and this took place at a payroll company in Montreal, Canada. And this is a company that was developing software that ran on, at the time I learned about it, they originally ran on an older IBM proprietary computer technology. I believe it was AS400s or some technology like that. They were mini computers, super mini computers running a lot of data-centric transactional systems. So this company had a payroll system that ran on AS400s, and they were migrating it to a multi-tier web architecture using WebSphere technology, which is IBM middleware. And that WebSphere technology was running on Unix boxes R6000s. So the payroll company wanted to port their payroll application from the AS400 world to the AIX world. So to that end, they hired 3 young and energetic programmers from a local university, not McGill, but Sherbrooke actually. Wonderful, wonderful programmers. These guys could program like the wind. These people really, the programmers loved unit test frameworks. They loved test-driven methodologies, but they had absolutely no commercial software engineering experience. So you can imagine this group of developers, no software engineering experience, but were very keen on using these tools and methods. So they start working on this migration. They start working on this port, and they put a chart on the wall. This is a chart to show their progress. And the chart basically indicates passing unit tests over time. So if you start at the beginning, you have maybe 5, 10 unit tests. Then after a few days, you had 30, 40, 50, and it goes up like a straight line, a beautiful line. And they get into the point where there's hundreds of passing unit tests, and management was excited. Management had never seen such fantastic representation of a progress of a project before. And the team was just, they were churning code out there, and they're getting passing unit tests, and it was all looking fantastic. However, once the number of unit tests started hitting somewhere in the 1,000 to 1,500 range, around then, some of the managers were starting to get a bit apprehensive. Because how could we see so many passing tests but not see any working payroll transactions? Like, what's wrong with the system? They had lots of passing unit tests, but they couldn't see or demonstrate any working payroll transactions. In fact, one of the managers took a 3-day public course that I offered called Software Testing Methods and Tools that was offered publicly in Montreal. And this person took the course for 3 days to try to learn about testing. And then he asked me to come and take a look at his company, to look under the hood, help him understand what was wrong. I thought it was a fantastic opportunity for me to sell some consulting services, but I made a foolish mistake. I went there. I had to pay for parking. I thought, okay, they're going to validate my parking. They're going to buy me a lunch. This is going to be a nice meeting and learn about their system. But when I got up there, as soon as I walked in, some of the developers saw me. They sort of welcomed me. They introduced me. They brought me right into their coding environment and dove right in, trying to show me what they were doing. And they were all so proud of the work they were doing. It was really awesome. And I'm looking at it. And all I can see when I'm looking at their tests are tests that basically exercise the code. So they had a snippet of code, and then they had a test that exercised the snippet of code. And all the code was tested that way. And what they had done was they had set up tests that exercised the code. And every chunk of code that they created had an associated test. And the test basically confirmed that the code did what it was programmed to do. Now, after a while, you start looking at this test after test after test, and the tests demonstrate that the code does what it was programmed to do, but none of the tests explicitly checked to see if the code did what it was designed to do or if the code did what it was required to do. They had just created tests to see if the code did what it was programmed to do. Essentially, they were testing the compiler. They were testing, did the compiler generate the code, the opcodes that matched the code that was written that executed correctly. It wasn't testing, did the business needs get met by the code, or was the design implemented correctly by the code? Their code proved a lot about the software, and they had showed me a system which was, frankly, one of the most robust systems that I ever saw in my professional career. There was no way you could crash the system. It was robust, it was solid, but it just didn't work. It didn't work. And it was very easy for me to tell them what they were doing wrong. And I said, you can't just test the code that way. Yes, structural tests of code like that are interesting things, and they have regression value. So if you write a test like that now, and then you change the code later, the old test should still pass. It's got regression value. But you should, for every single feature you implement, or every story you implement, or every requirement you implement, you should also have tests to make sure that the requirement does what it's supposed to do. And in fact, for many user stories, we break those down into whole categories of acceptance tests. So we have acceptance tests based on what the requirements are, and we look at normal, alternate, and error flows on those. So we get many acceptance tests for each requirement. We get, coupled with that, tests based on reality, and the reality is tests based on the real code changes that have to be done, tests based on the real environment that the software is going to be run in, and tests based on the real work that the user is going to do. So that's reality-driven tests. So we have requirement-driven tests, reality-driven tests, and structural tests like the ones that were being developed by these programmers. So all of this said, everyone thanked me and wished me well. I didn't get 1 minute worth of consulting out of this. I didn't get a lunch. I didn't get my parking validated, but I did get a pretty good cautionary tale. So the moral of the story is that when you're developing unit tests, don't create tests that show that the code does what it was programmed to do. Generate tests to show that the code does what it was either designed to do or required to do. And this could be, by the way, functional or non-functional. When I say non-functional, usually I mean things like performance, scalability, memory use, CPU use, stuff like that. So not the basic functionality all the time. And just a couple of notes now on the summarizing what's the basic process steps that are followed in unit testing. So there's just two approaches to doing this. The first one is traditional unit testing. And there is nothing wrong with traditional unit testing. This is called test after development, not test-driven development. Many programmers practice this approach. This approach would have been encouraged up until the mid-2000s, as I mentioned before, because it would have been natural to do this approach. Programmers who are really good at traditional approaches create solid and robust code, as well as a test-driven developer. So I would say traditional approaches are great. And if I have programmers working with me who are very good at traditional unit testing, I find it difficult to switch them to test-driven approaches. There's certainly not always much of a benefit. As long as they're doing good unit testing, they're doing good unit testing. So the traditional approach is to write the code, to plan the tests, so to figure out what are the risks you want to study, platforms you want to study, conditions you want to study. Then basically run tests, identify defects, regress, debug and troubleshoot critical defects, and rework the code. And then the last one here, I'm going to move my little picture up here. Implement the corrections. So rework to implement the corrections. So that's sort of the basic traditional approach. This is test after. You write the code, then you write the test, then you do the rework. Test-driven approach, follow-up would be moving on to the next activity. Next approach is the test-driven one, where you start off, you plan the tests, so you know what the requirements are, you know what the goal is, you know what the reality is. You make a list of the test objectives, and you organize your development into testable chunks. So you're going to program it basically one test at a time. Build a test, which could include code, data, test harnesses, stubs, drivers, stuff like that. Code, so you build the test. You code the simplest code to pass the test you just made, and you run the test, make sure they pass, correct it as you need, and continue until you have no more tests to build. So the test-driven approach is you create the test, then you write the code. Traditional approach is you create the code, then you write the test. Both of them perfectly valid approaches. I've had, as I said, difficulty imposing test-driven approaches on programmers who are very good at test-after development, but I encourage people, especially the new generation of programmers that are good at test-driven approaches, practice it day by day. Do it. It's a natural way to develop software. And that's the end of that section. I thank you very much.